I'm Rob Lamb. I'm Director of the JBA Trust and Chief Scientist for JBA Group. We're a not-for-profit foundation set up in 2011, and our core funding comes from the JBA Group of companies, but we're legally independent of JBA and a registered charity with an independent board of governors. Our objectives are to promote and support science, research and education in the fields of environmental risks and resources management, and we're particularly interested in work relating to the water sector. It can be very difficult to understand how water flows in rivers and how we should design bridges and culverts, so we built a simple scale model that helps us to demonstrate the principles of good hydraulic design.
Welcome to the JBA Trust demonstration Flume. This bit of kit is designed to show how rivers behave, and particularly how rivers behave in flood and how rivers behave when we have culverts and bridges and other obstructions in the river. Just to explain the kit to you, what we have here on the right, this black box here contains 150 litres of water, and I have some pond pumps there in the bottom. When I turn these pumps on, they will pump water along the bottom of the flume, and it wells up here in this stilling chamber, and then the flow will go from left to right down the channel and then weir over at the end, and the water just in a continuous loop being recycled. We've got some colouring in the water to turn it nice blue so you can see the water. During the demonstration, main thing is concentrate on what is happening above this level. This is the bed of the channel. What is happening below there isn't relevant to the demonstration. So I'm going to turn the pumps on. It'll just take a while for the pump for the flume to prime. What we have here is a section of open channel. It's a rectangular section, constant gradient, and it's made out of this engineering perspex. Now this looks pretty smooth at this scale, but if this was scaled up to a real river, this would be equivalent to a fairly rough concrete. So now the flume is primed, we can have a look at the water level, and you can see in this central bit we've got a fairly straight water surface, and we've got a fairly constant depth as we go along the channel. That is what we call in hydraulics uniform flow depth. It's the flow we would expect in a river if it's fairly straight, of constant section and roughness. Now that in itself is not particularly interesting. What I'm going to move on to now is the effect of building things in or across the channel. And I'm going to start with weirs. This is a weir. This is what we call a broad crested weir. This is 5 centimetres high. It's called broad crested because the crest there is fairly broad. Now weirs are put into rivers to raise water levels, either to make a river navigable, to allow us to abstract water, although the most common purpose was historical, to drive mill wheels. So I'm going to put this section in, and what I want you to observe is the effect it has on water level and also the speed of flow. As you can see at the moment, the flow is travelling fairly fast down this channel. As I put it in, you can see it acts as a dam to the river, so the river has to back up before it can rise high enough to flow over the weir crest. And you can see now, if we look at the water level upstream, it is now considerably higher, and 10.2, so about the height of the weir. And this is what we call the backwater effect. By putting this barrier to the flow, we're backing up the water. If this flume was long enough, as we went upstream, we'd actually find the difference between this before and after level would decrease, and there will be a point upstream at which the levels are the same, i.e. this weir no longer has an effect on the flow. Now, one thing with weirs, while they are there to raise water levels, we might want to just minimise how much it does raise the water level. And one way of doing that is to increase the length of the weir. And this is the same weir in all aspects, except it's got a longer crest. So if you look at it in plan, you can see it's diagonally across the river. And that should mean that our increasing water level is reduced. So let's just see what happens. So again, we just need to allow the water to reach equilibrium. So you can see the water level rising. And you can see it's slightly lower. And the longer you can make that crest, the more we can reduce the water levels. So now moving on to bridges. So this is an arch bridge. There you go, you can see a twin arch. And in plan, you can see it's in parallel to the riverbank. And the cross-sectional area of these two arches combined is 50% of the cross-sectional area of the channel. So that means this bridge represents a 50% blockage ratio. So if Alex could just mark where the water level is at the moment. So that's without the bridge. Here comes the bridge. Water level rising due to the constriction. So we've still got an air gap above the soffit. And the water level has risen. So that was that bridge in plan, parallel to the river. This is the same bridge, so a twin arch again, but the difference is the arches are now skewed relative to the flow. So that's going to make it more difficult for the flow to get through the bridge. And let's see what effect that has. And you can see where the water level was with the non-skewed arches. With the skewed arches, the water level is just slightly higher. So clearly, if we were designing this as a new bridge, we'd probably try and avoid that skew, and we'd also try and make these arches bigger. Okay, the next thing I want to demonstrate is the effect of culverts on flow and level. Here we have the Flume running as an open channel. You can see there the level is 4.5 centimetres on the upstream gauge. I'm going to put this culvert in. This is an arch section culvert. The area of that arch is 50% of the cross-section area of this channel, so it's what we call a blockage ratio of 50%. So put the section in. Notice now how the flow is having to contract into the entrance. Notice the steep water surface gradient here. Notice the barrel along here isn't flowing full, and that we have a free discharge at the downstream end. If we were designing a new culvert today and we wanted to follow best practice, this is how the culvert should look like during our design flood flow. So during a 100-year flood flow, we're not expecting the culvert to be flowing full. And the reason for that is that it allows debris to go through the culvert. Here's a floating tree or something in the manner. And if you look at the debris, and you can see it safely flows through the culvert. It'll also help if we keep the culvert straight and we have no section of the culvert. Now you might ask is, why don't we use all this extra space? We've spent all this money on the culvert and we're not using all the cross-sectional area. Well, the problem with that is to get a pipe like this to flow full, there's a good way of doing it and a bad way. The good way is to raise the water level to pressurise the pipe. I can't actually demonstrate that in this Flume, but that would involve raising the water level 3 times the height of the culvert. In a river culvert, that's actually very difficult to do because normally the channel banks are lower. The other way of getting a pipe to flow full is if we're under what is called tailwater condition. So this is where the water level downstream is backing up for some reason. And here I'm going to back the culvert up. And you can see as I raise the tailwater level, you can see now the culvert is filling. And while that's good in the sense I'm now using all the cross-sectional area available, notice though the effect on water level. To achieve the same flow rate I need an even higher water level. So in this case actually using the whole cross-sectional area of the culvert is actually no better and in fact worse than only using half the cross-sectional area. Now one thing with culverts is they can be prone to blockage by debris. One way of reducing that is to flume the entrance. These are cheeks. These are 1 in 6 cheeks, i.e. That distance there, this long length is 6 times that. And if I put these cheeks in, what we should see is the water level there will drop slightly, and I'll also show the benefits in terms of debris management. Much smoother flow now as we go into the inlet. The water level's dropped a little bit more at the inlet. The culvert is still having a backwater effect, but it's a reduced one. A secondary advantage of this is debris. Here's some more debris. Here the fluming helps direct debris to align with the flow and the barrel of the culvert, and even quite large debris should go through. Now debris is a concern at culverts, and this is why you often see screens. And here's a screen. So this purpose is to prevent debris getting inside the culvert. So these bars will collect debris that could have jammed inside the culvert. So I'm going to put this on. Just notice the effect it has on water level. And you can see the water levels increasing. Because I'm further reducing the cross-sectional area, these bars are reducing the flow area, so I need a higher headwater level to get the flow through. The thing to remember with screens is they won't actually be like this during a flood. However well designed they are, they will collect debris. Here's some floating debris. This is just representing a mass of leaves and twigs we get in any river. They'll come down the water course, and of course they'll collect on the screen. And even though we'll try and get that debris off, it's very difficult, and particularly this screen design, it's exceptionally difficult to keep the screen clear. And if you notice that once the screen starts to block, just look at the dramatic effect it has on the water level. But our designs have to be realistic, and while the $6 million question is how much debris we allow, certainly allowing no debris is unrealistic. Now that screen is not a particularly good design, mainly because being vertical and with these crossbars it makes it very difficult to rake. This is the kind of device that we use, very low tech, but it's the best we have. So if you're trying to rake that screen, you can see 2 immediate problems. One is that the tines of the rake are going to catch on the crossbars, but also I'm trying to rake debris in the vertical against a very powerful horizontal force. A much better screen design is this one. You can immediately see there's much wider bar spacing. There's also a lot more net cross-sectional area. In fact, this has got 3 times the area between the bars as the cross-sectional area of the culvert, and that's the minimum you should have for a good screen design. I'm going to put this screen in. First thing you'll see, it has a much less effect on the upstream water level than the previous screen. there still is some effect, but it's much reduced. Secondly, I'm now going to put some debris on this screen, because even with the better design, we're still going to get debris collecting on the screen. And yes, the blockage is having an effect, but whereas before with that other screen design, we're up here with this amount of blockage, here we're much lower. So while we don't know exactly how much blockage to allow, certainly we know it shouldn't be zero, and certainly you want to make sure the screen can be cleaned. The final thing with screens is that they're put in for security reasons, and that's to so they don't present a health and safety risk. The risk comes from two sources, or the potential risk. One is being inside the culvert during a flood or suffering from asphyxiation. The best way of reducing that risk is to have a very short culvert, so that even if somebody is in the culvert, they could get out. Another potential risk is someone falling into the river and being swept into the culvert. And here we have our demonstration duck, and this duck is in the river. He comes towards the culvert. You'll notice it is swept through the culvert. So not a very pleasant experience for the duck, but it only took a few seconds to flow through. Plus, because this was a long straight culvert, there was nowhere to trap the duck inside the culvert. However, when we put a screen on a culvert and somebody falls in upstream, they will now be trapped against the culvert screen. And that actually can be a higher risk than being swept through the culvert, because there's a huge amount of water pressure acting on this duck. And plus, limbs and so forth can be caught on the screen. Plus, of course, there's floating debris coming down and collecting on the screen. So, if screens are going to be put on culverts for safety reasons, we have to make sure a rigorous risk assessment is done.